Good evening, boys and girls, and welcome to another lesson on Technical Sciences, grade 12. It's the 15th of September, and we are continuing again with organic chemistry. I hope that you have your pens ready as well as your papers ready so that we enjoy this particular lesson. Right. Remember now, in the overview of our lesson for today, we are still going to continue with nomenclature, so we'll learn that and we will do a couple of questions on nomenclature, and I will also give you tips on how to prepare for your trial examination as well as the examination at the end of the year. So I hope that you are really ready, and we are continuing again with organic chemistry. Now, this is basically the same overview that I gave you yesterday. And yesterday we dealt with alkanes. And now we will be dealing with alkenes as well as alkynes in this particular lesson. So we will be doing that throughout the week up until we also deal with haloalkanes, aldehydes, ketones, alcohols, as well as carboxylic acids. So I have kept this because I want us now and again to revert back to the definitions that are important in this particular topic as and when we are learning this topic, and hence I'm going to keep this for the duration of the week, as well as this particular table on functional groups of various homologous series. Right? So I want us now to go straight into dealing with isomers. Now, yesterday I gave you a definition of an isomer, or a definition of what we refer to as a structural isomer. Now, you will remember that when we define the term structural isomer, we say those are organic compounds with the same molecular formula but different structural formula. So they are organic molecules with the same molecular formula but different structural formula. In other words, when you look at isomers, you are looking for molecules that will have the same molecular formula, but then those structures again, they must have different structural formulae. Right, they must have different structural formulae. Now, let us say I give you a structure of this particular compound, and this compound is butane. And before we even go further, I just want us to discuss how did I get to this particular name, which is called butane. First, you check the number of carbon atoms here. It's 1, it's 2, it's 3, it's 4. And these carbons are bonded to each other. And this becomes the longest carbon chain without breaking. It has 4 carbons, and we refer to that as a parent chain. Now, because the longest chain without breaking, the longest chain of carbon atoms that follow each other by bonding is 4 carbons. Then the prefix, it means the name is going to start with but altogether. And then because this is an alkane, and how do I see that this molecule belongs to the homologous series alkanes, is because I can see that I have single bonds between carbon and carbon atoms. So it's a single bond between carbon and carbon atom throughout. And therefore it is an alkane, and the name will then end with ANE. So remember now, the full name will have that that prefix as well as the suffix, and the full name will then be butane. Now, my dear learners, what do you see here? What you see here is a structural formula. I will just write SF. It's not the abbreviation, but just for us not to waste time. So this is the structural formula. Now remember, when we want a structural formula, you actually need to draw altogether all the atoms that are in that molecule, and furthermore, you need to show which atom is bonded to which. That is what the structural formula is. But I can ask you again, what is the molecular formula of butane? Remember, what we see here is the structural formula of butane. So what is the molecular formula of butane? Remember, with the molecular formula, all we do is we just count how many of each atom are present in this particular molecule. So I can see that I have 4 carbons here. So this is going to be C4. And then I'm going to check how many hydrogens I have in this molecule. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In other words, for butane, I have 4 carbons, but then I have 10 hydrogens. Now, if I want an isomer of butane, it means I must draw another molecule which is not butane, but it must have the same molecular formula as butane. It means an isomer of butane will be a molecule that is also a C4H10. So it will have the same number of carbons and hydrogens as butane, but I won't draw it the same way as butane. In other words, the structural formula must be different. Now, how do I create an isomer of a molecule like butane? Now, when you look at butane, butane is actually a straight chain alkane. We classify it as a straight chain alkane. Why? Because there are no branches. The carbons are arranged in a straight chain. You can see it's 1, 2, 3, 4, and they are bonded to each other without any branching. So if I now want to draw an isomer of butane, meaning I still want to keep the number of carbons the same and the hydrogens the same, then I can now make my chain not to be a straight chain anymore. In other words, I can make it what we refer to as a branched chain. If it is a branched chain, it means one of the carbon atoms is going to be branched altogether. It won't be following in a straight chain pattern. For example, in this particular molecule, can you see there what I have done? I put carbon 1, carbon 2, carbon 3. Now, there it's 3 carbons. And what do I do to the other carbon? I attach it to another carbon there instead of there, because if I bonded it to that carbon there, then it would give me the same molecule as butane. So it would still give me a straight chain. But if I bond it to another carbon there, then the chain, we say it is branched. Why are we saying it is branched? Because now the longest chain without breaking is now carbon, carbon, carbon. If I wanted to go to that carbon now, we can see that the carbons now are breaking. So I can't exactly go to that carbon without breaking. So without breaking, it's 1, 2, 3 carbons. So that carbon now is a carbon that has broken from the parent chain. And if it is broken from the parent chain, it means it's not part of the parent chain altogether. So the longest chain without breaking there is 3 carbons. So it means that particular carbon there, it's actually what we refer to as a substituent altogether. Why is it a substituent? Because it does not form part of the parent chain altogether, right? So now it is like a branch, just like when you think of a tree has a stem. Can you see there? This is a stem, and then there again now I have a branch altogether, which emanates from where? From the stem. So that carbon there is acting as a branch because 1, 2, 3 is actually my stem, which is the parent chain. And we know the parent chain gives rise to the branch, or we know the main stem will give rise to a branch. So this chain now we say it is a branched chain. It's not like this chain. So if it is branched, then I'll put my carbon there. Then the only thing that will be left will be to put hydrogens. And remember that each carbon atom must have 4 bonds. So I'll put 1, 2, 3 hydrogens. There's the 4th bond. Then around this one, it will be 1, 2, 3. The 4th bond will be that one altogether. Then around this carbon, I'll put a hydrogen, is 3 bonds. The 4th bond is that one. Then on this carbon, I have 1, I have 2, I have 3. Then I have bonded that particular carbon. And that particular carbon must also have 4 bonds altogether. So it is attached to 3 hydrogens. So it's 1 hydrogen there, 1 hydrogen there, 1 hydrogen there. So it's 3 bonds, and there is the 4th bond altogether, my dear learners. Right. So this molecule is definitely correct. Why? Because each carbon around it, it has 4 bonds. Then what else am I supposed to check here? I'm actually supposed to check if this molecule is really an isomer of this one. Now, firstly, I can see that the structural formulae are different. So I'm happy with that part to say, okay, with these 2 molecules, the structural formulae is different. Then, does it qualify as an isomer to that one? I then check the second condition is if the molecular formula is the same. Then for the molecular formula, remember, I just have to count how many of each atoms are present in this particular molecule. So in this molecule, you can definitely see that I have 1, 2, 3, 4 carbons. So that will be C4. Then the number of hydrogens, I have 1, 2, 3, 4, 5, 6, 7, plus these 3 hydrogens. So it's also H10. So I can see again that, oh, the molecular formula of butane is the same as the molecular formula of 2-methyl propane. So these 2 molecules, they have the same molecular formula because both of them are C4H10. But the structural formula is different altogether. So because it meets these 2 criteria, it means these 2 molecules are classified as structural isomers altogether. Then we can go further and ask you, what type of structural isomers are they? Then you are going to say these are examples of chain isomers. Now, why are you saying these are examples of chain isomers? Because they are organic molecules with the same molecular formula, but a different type of chain. So these 2 are organic molecules with the same molecular formula, but different types of chains. And because the chains are different, then these molecules are examples of chain isomers altogether. Why are we saying the chains are different? Because that one is a straight chain, but this one is a branched chain. Are we together? So when you go back, and that is why I have kept the definitions here as well, we can see that when we are talking about chain isomers, we say they are organic molecules with the same molecular formula, but different types of chains altogether. Right. Now, in the same breath, my dear learners, I now want to teach you how to give a name to this particular molecule, and we call that an IUPAC name. So let us check, how did they get to the name actually being 2-methyl-propane? Remember now, according to IUPAC rules, we must first get the parent chain. We must first get the parent chain. So the parent chain is that longest chain of carbons without breaking. So I have 1, 2, 3 without breaking. My dear learners, hear me well. The number of carbons here, it's definitely 4, but without breaking, I actually have 3 altogether. So the parent chain is made up of 3 carbons, and therefore it's a prop altogether. So let me just write it there. It's a prop. I want to show you how we actually start with the name. So I start with the parent chain, which is a prop altogether. And then I then check that, okay, to which homologous series does this molecule belong, right? So this molecule, I can see that it's single bonds between carbon and carbon atoms. So this molecule belongs to the homologous series alkanes. So it is going to end with ANE altogether. So I am done with the parent chain. Now, after I have read the parent chain, you can see that I had not counted that one altogether. So when you give a name to a molecule, you check, do I only have the parent chain? If you have the parent chain only, then you will just give it as a parent chain. But there I can see that from my parent chain, then I had not counted that particular molecule. Rather, I have not counted that particular part of the molecule. So that part of the molecule is a substituent altogether. It's a substituent. We call that a substituent. And these substituents, we say they are, as you see it there, it's actually what we call an alkyl group altogether. It's an alkyl group because it's actually short of 1 hydrogen. For example, if this was CH4, I would have called this methane altogether because it would have complete number of hydrogens. But there it's a CH3, so there is 1 hydrogen that is not there. As a result, instead of calling it methane, we will then call it a methyl group. So this alkyl group, it's actually called a methyl group. This alkyl group is called a methyl group. You don't say it is a methane. So your substituent will always come before the parent. So this substituent will come then. So it is a methyl. Right. So you are done with the parent chain, you are done with the substituent. Now, what is important is you also need to give us in which position is your substituent. So every time when you number the parent chain, you must number it in such a way that, and this is an IPEC rule, my learners, you must number it in such a way that the substituent is on the lowest numbered carbon. So it must be on the lowest numbered carbon. So if I number from left to right, I will say it's carbon 1, carbon 2, carbon 3. It means this substituent is attached to this carbon. This entire part, which is the substituent, this entire methyl is attached to that carbon. So it is attached to carbon number 2. So we will then call it 2-methyl propane. So why are we saying 2? Because this methyl is attached to carbon 2 of the parent chain. So we call it a 2-methyl because we need to give the position of the substituent. Now, I can't actually leave it as a, let me just do this. Right. So when you actually do it, you can't just say this is a 2-methyl. I'm sure you will remember from your class that you must actually put what we call a hyphen, and a hyphen must always come between a letter and a number. So those are some of IUPAC rules. So I couldn't just leave it as 2-methyl propane. It's actually 2-methyl propane. But by pronunciation, we actually say 2-methyl propane. But by writing it, it will be 2-methyl propane because you need to give us the position of that methyl group. And then after noting the position, you make sure that there is a hyphen or what you call a dash between a letter and a number. And it doesn't matter how you had numbered actually here. Even if I numbered 1, 2, 3, it means that would still be my substituent there. And this substituent would then be on carbon 2. Even if I numbered 1, 2, 3, this would be my substituent. It will still be bonded to carbon 2. So these are isomers because they have the same molecular formula but a different structural formula. And we classify them again as chain isomers because they are organic compounds with the same molecular formula but a different type of chain altogether. Right, let us look at pentane. Now, there is pentane, and why are we saying it is pentane? Because it's 1, 2, 3, 4, 5 carbons long. So the parent chain has 5 carbons, so it is pent. And then single bonds between carbon and carbon atoms. So this is an alkene, so the name ends with ANE. Now, do I have a substituent here? And my answer is no, because all these carbon chains here, I can say it's carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. There is no other carbon that is there except the one that is on the parent chain altogether. So you don't have a substituent. So this name is only made up of the parent chain. So the substituent will only come in when you have this situation there where there's a carbon now that does not form part of the parent chain, right? Then if I want an isomer of pentane, what do you suggest I do? Then I would have checked and I would have said, okay, but here I have a straight chain alkane, right? The pentane is a straight chain. So what I can actually do is to then say, okay, let me make this chain to be branched. Let me shorten the chain. Let me shorten the parent chain so that I can take one of these carbons and actually make it a substituent. Then it is going to work altogether. So that is the trick that I want to give you, to say shorten the chain. So it was 5 carbons long, make the parent chain to be 4 carbons long so that one of the carbons is then made a substituent altogether. So you could actually do this. Let us look at this one. Can you see now? I have shortened the chain to be 1, 2, 3, 4 carbons long. So the longest chain without breaking there has 4 carbons altogether. And what did I do to the other carbon? I have made it a substituent. altogether. So if you look at this particular molecule and you compare it to this one, let us check if they are really isomers. So how many carbons do I have actually? I have 1, 2, 3, 4, 5. So it's 5 carbons, and you can check the hydrogens for yourself. It's 12. 1, 2, 3, 4, 5. Okay, let me start it this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this molecule is a C5H12. So the molecular formula is C5H12. Then let us look at this one. How many carbons? 1, 2, 3, 4. Remember now, the transformation from there to there is that one of the carbons that was there, I made it a substituent. There it's a substituent now. So it's still 5 carbons. So it's C5. Hydrogens, it's 1, 2, 3, 4, 5, 6, 7. Plus this 3, it's 10. Plus this 2, it's 12. So I can see again that the molecular formula here is actually a C5H12, right? There we go. There we go. Right, the molecular formula there is a C5H12. But is the structure the same? And my answer is the structure is definitely not the same. Why? Because this one was 5 carbons long without a substituent, or basically without a branch. This one is 4 carbons long with a substituent, right? So the molecular formulae are the same, but the structural formulae are different. So these molecules are classified as isomers altogether. Let us give a name to this one. What is the longest chain without breaking? Remember, I said when you give an IUPAC name, you start with the parent chain. You start with the parent. So it's 1, 2, 3, 4. So it will give me bute. Everything is a single bond between carbon and carbon atoms, so it is an alkane, so the name will end with ANA. So I'm done with the parent chain, but I can see that now I have that part which I have not counted, which did not form part of the parent chain. So that is our substituent, and we can see it's a substituent with 1 carbon. And it's an alkyl group. So the name ends with YL because this is an alkyl group. So for 1 carbon, it's meth. And then because this is an alkyl group, then it's a methyl. Or rather, the name ends with YL. Right? So for 1 carbon, it's meth. And then I have the fact that I know that it's an alkyl group, so the name ends with YL. So this is going to be a methyl. Then I check where is that methyl substituted. I can see, rather, where is that methyl attached? It is attached to this carbon, which is carbon 2. So I'll put a 2B for the methyl, and then I need to put a dash, right? A hyphen. What is the reason for that? Because the IUPAC rule says there must be a hyphen between a letter and a number. So the name of this compound will be 2-methyl-butane altogether. Now, what if you numbered 1, 2, 3, 4? Then you would have found that it gives you 3-methyl-butane, right? So the answer would have been 3-methyl-butane. And this one is the only one that is correct. This one, okay, for this part, you will get a mark, but for this part, you will not get a mark. Why? Because when you number like this, then basically what you are doing is you are now making that substituent to be on the highest numbered carbon. So by numbering from right to left, then you make this substituent to be attached to carbon 3. And that is not according to IUPAC rules, because you must number in such a way that this particular substituent will be on the lowest numbered carbon. So it will be best for you to number from the left up to the right, because then that substituent will then be attached to carbon number 2. So that one becomes incorrect, and hence I'm going to remove it for you. I was just trying to show you why you can't number like that. Then look at this one again, my dear learners. So now you have branched. What else can you do? Someone can say, but I can shorten the parent chain even further. Instead of making it 4 carbons long, then let me make it 3 carbons long. If you now make it 3 carbons long, it means the 2 other carbon atoms are going to form part of the substituent. So you saw I started with 5 carbons, then I shortened to 4 and made 1 of these carbons to form part of the substituent. So if I want another isomer of pentane, then I can go and shorten the parent chain even further and make it 3, so that this entire thing can now form part of the substituent. So let us check there. So now my carbon chain is now 3 carbons long. So it is 1, 2, 3. Then what did I do with the other carbon? I attached it there as a branch. I attached another carbon there as a branch. So what is the longest chain without breaking? It's 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Either way you go, the longest chain without breaking is 3, right? 1, 2, 3. For these ones and that one, then I have broken. So I start with the parent of 3. So it's a prop. Single bonds between carbon and carbon atoms, then this is going to give me the fact that this is an alkane, so the name will end with ANE. Then if this forms part of the parent chain, it means this part is a substituent and this part is a substituent. So my first substituent is a methyl on carbon 2. My other substituent is a methyl on carbon 2. Can you see that now I have 2 of the same substituent? What do I mean I have 2 of the same substituent? It means I have 2 methyl groups. So if I want to now include it on the name, I won't say 2 methyl, 2 methyl. Why can't I say 2 methyl, 2 methyl? Because this is the same substituent. So because it's 2 methyl, then I'm going to say it's a dimethyl. Instead of saying 2 methyl, 2 methyl, I will just say this is a dimethyl to show that I have 2 methyls as a substituent. Then what am I supposed to do? Remember, you need to give us the position of the substituent. So the position of the substituent, one substituent is on carbon 2, there it is. Again, another methyl group is on carbon 2. So I show both of the numbers. I don't say, but they are both on carbon 2 and then I show 1, 2. No, that is not what you do. You show us, oh, the first methyl is on carbon 2, there it is. The second methyl again is on carbon 2, then I show it again altogether. Then you can see that there is a comma, right? So what is the comma for? The comma is to say, it's actually an IUPAC rule to say between a number and a number, you have to put a comma. So I have a 2 for that substituent. I have a 2 for this substituent. So between a number and a number, then I have to put a comma. Then I already had that part on dimethyl. Then here I have a letter and a number. Then I have to put a hyphen, which you normally call a dash. So between a number and a number, you must put a comma, and between a letter and a number, you have to put a hyphen altogether. So the full name here is going to be 2,2 dimethyl propane. Now let us check if this molecule is an isomer of pentane and if it is also an isomer of 2-methyl-butane. What I can already see is that the structural formula are already different, right? So is the molecular formula the same? So I check the number of carbons. I have 1, 2, 3, 4, 5. So in total, I have 5 carbons. So for hydrogens, I have 1 plus 3 is 4, 5, 6, 7 plus 3 is 10, 11, 12. So this is also a C5H12. So all these molecules, they are C5H12. So they have the same molecular formula, but different structural formulae. So they are classified as isomers. And specifically, they are classified as chain isomers because the chains, they are organic molecules with the same molecular formula, but different types of chain. So if I ask you how many isomers does pentane have, you can't say, oh, pentane, it has 2 isomers. No, we actually say pentane has 3 isomers. We actually include it by itself altogether, right? Then I want us to test our knowledge here. And we are required to give the IUPAC name for this particular molecule. Now, I also choose this molecule because it is going to help you to learn something else. What you actually see there, it's actually a condensed structural formulae altogether. It is a condensed structural formulae. So basically it's just carbon bonded to 3 hydrogens, then another carbon bonded to that carbon, and then this carbon is bonded to a hydrogen, and this carbon is bonded to CH3, and so on altogether. You can actually just look at this and turn it into a normal structural formula. So you could have just said, oh, the first carbon, it's actually 3 hydrogens, right? Then the second carbon, there it is, it has a hydrogen, it also has a CH3. Then you have this carbon, it has 2 hydrogens, and then you have this carbon and it has 3 hydrogens. Right, so we are basically, this and this is the same thing. So we are required to give the IUPAC name for that molecule. So what is the first thing we do? We always look for the parent chain. So the parent chain is the longest chain without breaking. So it's 1, 2, 3, 4 carbons long. Yes, there is a carbon there, but you see this one is not counted in the parent chain because there is a break. So the longest chain without breaking is 4 carbons. In other words, it is a bute. And then I have single bonds between carbon and carbon atoms. Single bond between carbon and carbon atoms. So it is an alkane, so the name will end with ANE. Then I check, okay, this is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4. Then I see that that particular carbon was not counted in the parent chain, so it is a substituent, and it's a substituent with 1 carbon, and it's actually short of 1 hydrogen, so it's an alkyl group. So because it's an alkyl group with 1 carbon, so it will be meth. And remember, alkyl groups, the name ends with a suffix YL. What else am I required to do here? I'm required to give the position of the substituent, and this substituent is on carbon number 2. So I'll put a 2 there. But what else is missing there? Remember, between a letter and a number, I definitely have to put a hyphen. So the name of this molecule is 2-methyl-butane. In other words, if this was multiple choice, the correct answer there would have been 2-methylbutane, and you would have received 2 marks altogether, right? Then I want us to look at alkenes for today, and that is the one that we are going to end our lesson with, and we will continue further tomorrow. Now, alkene is another homologous series. Remember again the definition for homologous series. It's a series of organic compounds that can be described by the same general formula and where each member differs from the next by a CH2 group. So the general formula of alkenes is CnH2n, and you will remember that the N actually represents the number of carbon atoms. Now, what is the structure of the functional group of alkenes? Remember now, when we talk about the functional group by definition, we say it is either an atom, a group of atoms, or a bond that determines the chemistry of a molecule. In other words, a functional group is actually what defines that particular homologous series. So it is actually an atom that shows us that this is a particular homologous series, or it's a group of atoms that show us that this belongs to a particular homologous series, or it is a bond that shows us that this molecule belongs to a particular homologous series. And with alkenes, how you see them is that you actually have a double bond between carbon and carbon atoms. So this makes it different from what we learned when we're doing alkanes, because with alkanes, we know that we get a single bond between carbon and carbon atoms. All together, my dear learners, right? So this is what makes alkenes to be different from the others, is because there's a double bond between carbon and carbon atoms. So that's what you want to show us. Then what else do you want to show us when drawing a functional group? Is to then show us that around each carbon I must still have 4 bonds. So if I have a double bond there, it's 1, 2, so it will be 3, it will be 4. For this one, it will be 1, 2, then it will be 3, it will be 4, and you don't include your hydrogens, because if I include the hydrogens there, now I have actually drawn the organic compound. Are we together? Right. So when we look at alkenes, right, I want to sort of give you an idea there. Now, there is no way that you can have an alkene with 1 carbon. Why can't you? Because with an alkene, you need to have a double bond between carbon and carbon atoms. So all our alkenes begins with at least 2 carbon atoms. So let us draw that alkene with 2 carbon atoms. So I would have shown carbon, carbon, and because it's an alkene, then it would be a double bond. Then it already has 1, 2, then the third bond, the fourth bond, the third bond, the fourth bond, and I will just complete with hydrogens. What you then definitely see is that this particular alkene, it means it is a hydrocarbon altogether. Why is it a hydrocarbon? Because this is an organic compound that contains only carbon and hydrogen atoms. This organic molecule or this organic compound contains only carbon and hydrogen atoms. Hence, hydro for hydrogens only, carbon for carbon atoms only. And that is why your definition, again, I told you it needs to include that term only. Then if I want to give a name to this compound, then I look again for the longest chain without breaking. That includes that functional group. So it's 2 carbons. In other words, it will be eth. And because this is an alkene, just like with alkanes, remember with alkanes, Because it was an alkane, the name ended with ane. So now, if this is an alkene, it belongs to the homologous series alkenes. It means the name will end with ene. So F for 2 carbons, ene to say it is definitely an alkene. So there's the structural formula, and this one is the molecular formula because we just count how many carbons we have as well as how many hydrogen atoms. Right. Then this one, it's actually what we call propene altogether, right? Why is this propene? I go and look for the longest chain without breaking. So this is carbon 1, this is carbon 2, and this is carbon 3 altogether. Then it means it's prop there. And I can see now my functional group, which is the double bond. Can you see it's actually between carbon 1 and carbon 2? But then when it's between carbon 1 and 2, we then just say it's on carbon 1. So you don't really need to specify then the position of that double bond. But at some point, you actually need to tell us the position of the functional group. But for this one, it's not necessary because it's actually this double bond, it can never be on any other carbon other than carbon 1. Because if I brought it this side, then this would be carbon 1 altogether. So the name would then just end with ene, so we'll call this propene, and that is the molecular formula, right? Rather, the molecular formula. And then you check again this particular molecule here. This molecule, if I wanted to give it a name, then I check, okay, the number of carbon atoms here is 1, 2, 3, 4. And this is part of the parent chain because it is the longest chain without breaking. So the longest chain without breaking is 4 carbons. So it is a bute altogether, right? It's a bute. Then we check, do I have substituent? No, all the carbons were part of the parent chain. In other words, then the name just ends with ene. Why does it end with ene? Because I have a double bond there, so it's an alkene. So can you see, my dear learners, this molecule is actually a butene. But there's something that I really want to indicate to you there. This is a butene. But because the parent chain is 4 carbons long, and then ene because I have a double bond there. But you see this double bond, it can actually, from how I've done this is carbon 1, 2, 3, 4. Right, this is how I've numbered. So it's between carbon 1 and 2. In other words, the double bond is on carbon 1. So I need to give them the position of the functional group. So the functional group is on carbon number 1. It's between carbon 1 and 2, but we just say then we take the lowest number. We say it's on carbon number 1. So if it is on carbon 1, if I just leave the name like this, then it's not going to help me. I need to indicate the position. And hence, all you do is you just break the molecule there and say, this is what the molecule begins with. This is what the molecule ends with. So in between, I'm going to put the position of the functional group. So the functional group is on carbon 1. That is why we say this is but 1. So what it begins with is but. What it ends with is ene. So between what it begins with and where it ends, we put the position of the functional group, which is carbon 1. Which is position 1 actually of the functional group. So after putting a 1, you know that now you have a 1 between a letter, and so the 1 is actually now a 1, a number, and a letter next to it. Then a number and a letter next to it. So according to IUPAC rules, remember now, you have to actually put a hyphen between a letter and a number. a hyphen between a letter and a number. So what is very critical is where do you put that one? So you just check, oh, it must start with but and it must end with ene. So you will put the position of the functional group somewhere there, rather in between those, and make sure that there is a hyphen between a letter and a number altogether. So in our next lesson, my dear learners, we are then going to continue with isomerism of alkenes, as well as deal with the entire alkynes altogether. Then we would have been done with our hydrocarbons. So for those that have just joined us for the first time in this particular topic, remember, all in all, for the preparatory examination, this particular topic is going to, the entire topic, organic chemistry, will be 85 marks, but this section on nomenclature only, where we are actually dealing with the molecules and, you know, just the basics of molecules, it will be plus minus 29 marks. So it's really an important section, and I want you to understand it, and hence I'm going quite slowly with you, and I hope that you are following, and we will continue tomorrow, right? And I always remind you, once you stop learning, you start dying, and hence we must always accept new knowledge and learn it as it comes. Remember again, send me your questions to STEMdigitalschool@africateamgeeks.co.za, and I will be able to assist you altogether. Thank you so much, and enjoy the rest of the evening. Goodbye.